All right, guys, so today we're going to do a little bit of review for the midterm, and then we're also going to do some complex numbers. First, let me start off with a bit of midterm stuff. So, like, one of the things you're going to have to do for your midterm is write a cheat sheet. I think that's part of the fun, or I should say, okay, not fun. That's part of the learning experience, right, is having to figure out what are you going to put on your cheat sheet, what size font can you fit on your cheat sheet, right? Like, I don't know, maybe you should get one of those like really precise printers and print in like 0.5 font and use a magnifying glass. What examples do you put on your cheat sheet? I've seen some students who just like, forget putting formulas, they just put whole solutions to problems. I think that's kind of cheap. Like, come on, but whatever. I'm not gonna I'm not gonna be the cheat sheet police here. But so some of the things you should probably put on your cheat sheet are, for example, trig. I can usually remember most of the trig stuff that I need, but then I'm a math PhD, so like I kind of should. I'm used to it. You guys might not all have all your trig stuff memorized, so put it all on the cheat sheet. For example, graphs of sine and cosine functions. So this is a bit of midterm review, and yeah, you probably want to put trig graphs, for example, so like know what the graph of sine or cosine looks like. Or maybe you don't need to graph it if you just have a unit circle, for example. So that would be another thing to put on there. Again, this is if you need it. Like I know the unit circle. I wouldn't need that. I don't have every trig identity memorized, and we do need some of those. So yeah, you'll probably want to put identities on there. Like I think if you open up your book, your textbook, on the first page, it's got a whole bunch of, on the inside of the cover, I think it is, there's a bunch of trig identities. So those are probably good to have at your disposal. Certainly if it's one that we've used in the class in an example on the homework, then you'll want that one. Let's see. I did one problem involving completing the square. So I'm going to advise that you guys know how to do that if any of you forgot. Obviously, you'll want to know any formulas we've covered. So like, for example, from, what was it, 5.5, you need to know like the fundamental theorem of calculus. You should know 1 and 2 and know the formula that is associated with that. Well, I guess there's one formula for fundamental theorem part 1, and there's another formula for fundamental theorem 2. So you should definitely know those. And then after 5.5, we did 5.6, and since a lot of you guys are going into engineering, I like the velocity problems, so be familiar with displacement calculations and displacement versus total distance. Like displacement, you should know that's the integral from, I don't know, time 0 to time 1 of your velocity, whilst total distance is the integral from time 0 to time 1 of the absolute value of your velocity. Okay, so those formulas aren't too hard to memorize. Maybe the trickier part is knowing how to take the integral of the absolute value of a function. Those can be kind of tricky because you might have to break them up into the regions where the function is positive versus the regions where it's negative. So like, for example, if your velocity v of t was t minus 1, then for, say the first 2 seconds, if I wanted to know how far did you go, what was your displacement, and what was your total distance. Well, let's just do total distance. So that would be the integral of the absolute value as t goes from 0 to 2, which is the integral from 0 to 2 of the absolute value of t minus 1. The absolute value of t minus 1, by the way, looks like this. Let's say this is 1, and this is 2. So actually, what I'm calculating here is the area under this graph, which actually you could just kind of calculate because it's 2 triangles. If we wanted to, we could just get the area of these 2 triangles. Well, they're each the same. Well, here, okay, so it's 1/2 base times height. Let's see, the base of this triangle is 1. The height is also 1. And there's 2 of them. So I'll put a 2 equals, oh, actually, it's just 1 times 1, which is 1. Right? The base, that's 1. The height, that's also 1. There's 2 triangles. Or, that was a geometric way of solving it. But not all shapes are necessarily going to give you triangles in the area. So let's say you didn't realize that, oh, that's just 2 triangles. We could use calculus. And I said before, the only really tricky part is breaking this integral up into where it's positive and negative. Or sorry, into where whatever's inside the absolute value is positive or negative. So you would have to write this as, all right, from 0 to 1, it's actually, we'll need a negative sign. And then from 1 to 2, we can just leave it as t minus 1. So that would be an example of a total distance calculation. You might notice, here, let's just see what this is. This integral is t squared over 2 minus t. Same with this one, t squared over 2 minus t. But we'll have to put a negative sign in front of this one and evaluate from 0 to 1. And then this one gets evaluated from 1 to 2. And if you go ahead and do that calculation, you'll get 1, just like we did when we did the areas. Yeah?
Could you repeat why there's a negative?
Yeah, so between 0 and 1, t minus 1 looks like this. And between 0 and 1, it's negative. So what does the absolute value do to a negative quantity? It makes it positive, which is the same as putting a negative sign in front of it, because the negative of a negative is a positive.
Mm-hmm. Would it be acceptable on the exam to find the 2 integrals, and then if one of them has a negative value, just put the absolute value of that, and then add those 2 together?
If you do it correctly, then yeah, then that would work. But if one of the regions, say, includes where it's both positive and negative, then that won't work. let's see. We did some good problems involving cones, pyramids, similar triangles. So make sure you can do those problems. Yes, and most recently, we had lots of fun doing polar graphs. And I spent pretty much considerable time on Friday actually graphing some of these guys. So you should be able, given a relatively simple equation, I'm not going to give you anything too crazy, but yeah, be able to come up with a polar graph. Doesn't have to be super accurate, but like for example, if I asked you for an area calculation in a graph, we have the area formula, namely 1/2 the integral from the theta equals alpha to theta equals beta of f of theta squared d theta is the area formula. And the hardest part usually is kind of knowing what the angles should be. So you don't have to draw a perfect graph, but it needs to be good enough to figure out what the angles should be should I ask you for an area calculation. You definitely should be very well versed with U substitution and integration by parts. So let me just, I'll write down the U sub formula. It says that f of u du is the same as f of u of x, u prime of x dx. That's the indefinite form, and the definite form means I can put, oh wait, no. If x goes from A to B, then this one goes from u of A to u of B. And as for integration by parts, of course, you'll want to know the formula u dv equals uv minus the integral of v du in the indefinite case. And in the definite case, I'll put an a and a b here, an a and a b here, and an a and a b here. So here, let's do, how about an example of what is this? Here's an example that combines both of these. So yeah, you can tell I probably like this example because it uses both of these techniques. So what if I had the integral of cos root theta? I think this is kind of like a homework problem. All right, so a bit of advice if you're looking at a problem on the test and it's an integral and you can't figure out how to do it, right? Like your familiar rules of integration don't seem to be helping you, then you start to think of the more advanced techniques that we've learned, namely these two. U substitution, and then integration by parts. Now, U substitution is the more elementary method, so I would probably try this one first. Right? Like, try some substitutions to see if you can transform your integral into something that you do know how to integrate. If that still doesn't help you get into a form you can deal with, then try integrating by parts. Try setting something equal to u and dv and seeing if that gives you something you can integrate. So yeah, but part of the challenge here is kind of being able to identify when you can use these techniques and then actually implementing it. So anyone? First off, I want to point out that right off the bat, as written, we can't do this one. So that would be the first thing you want to realize is there's no, like let's say you naively, here, so I'm going to write something that's wrong. What if you just said, oh, well, that's equal, okay, integral of cosine is negative sine of root theta. Yeah, if you just tried to say, well, integral of cos is sine, root theta here means a root theta here, why is that wrong? Yeah, it's because of the square root here on the theta, yeah. So if you tried to do that, you would see that's wrong. If you wanted to check your answer, or your supposed answer, you would see that when you took the derivative of this and applied the chain rule, you wouldn't get this. Okay, so the first thing you tried doesn't work. So next, we start trying to try some of these tricks. And I said the first trick to try is U substitution. And there's kind of one obvious substitution to do here. Root theta, yeah, okay. So yeah, let's let U equal root theta. And then hopefully you're used to this now. As soon as you write down what U is, then calculate what du is. And since root theta is the same as theta to the 1/2, I'll get a 1/2 theta to the negative 1/2 d theta. That's the same as a 1/2 root theta d theta. Well, we have a d theta, but we don't have a d theta over root theta. So this still requires a bit more trickery. Like, for example, I can solve this expression for d theta, and I get that d theta is the same as 2 root theta du. Still not a great substitution, though, because we're supposed to be putting everything in terms of u, but this still has a theta in it. But wait, isn't this exactly what we just said u was? So d theta is 2u du. Oh. So that's kind of the trick there. And once you've realized that, this becomes a bit more manageable. So let's plug everything in. That's cos of u. D theta is 2u du. And did that improve things? So yeah, is this something we can integrate now? If you were paying attention, you heard me say that this problem actually uses both of my techniques. So now, we have an integral that is well suited for integration by parts, actually. Oh, but I already used the letter u. Crap. Can't integrate by parts if I can't call something u. No, okay, well, actually, I'll just let u be u. Okay, u is u. How about that? Yeah. So we're going to let, here we go. So I get a 2 times u times cos u du And here, let's let u, we're going to let u equal u. And this will be my dv. OK, so u is u. Du is, well, du. dv is cosine u du. So v was sine u. OK. So what do we get? We get a u times v minus the integral of v du minus the integral of sine, which is something we can integrate. Integral of sine is negative cosine. So that's plus cosine. And we better put everything back in terms of theta before we write this as an answer. So this is root theta sine root theta plus cosine root theta. And if you have any time left on the exam, you should definitely check to see that this is correct. Like, I did this kind of fast. I wonder if I made...
You got to add the 2.
Oh, there's a 2. Thank you. OK, yeah, and plus c. OK, good. So there's a 2. There's a 2 in front of everything. All right, so let's put a 2 in front of all this, and a 2 in front of all this, and a 2 in front of all this. So we get a 2 root theta sine root theta plus 2 cos root theta, and then, yes, someone said a plus c. OK. And here, in fact, let me just check, just to make sure. I'm going to check real fast if I did this right. So taking the derivative, let's see. I'll get a 2 times 1/2 times theta to the negative 1/2 times sine of root theta plus a 2 root theta times cos root theta times 1 over 2 root theta, and then plus a 2 times a negative sine root theta times a 1 over 2 root theta. Let's see, these 2's cancel out. These 2's cancel out. These 2's cancel out. This is sine root theta over root theta. Yes. So these 2 terms cancel out, and the root thetas cancel out. OK, these guys cancel. These guys cancel. And what am I left with is just cos root theta. Good. All right. I did it right. Any questions? Yes?
What kind of notation should we use for the IDV part when we have a problem like this because the U is already being used?
Sorry, what kind of notation should we use for what?
For the IDV part,
oh.
the integration of because U is already being used.
Right. So you could use a different letter if you had to. Yeah, like we usually use U, but as you noticed in this problem, I already had a U, so you could use a W, a Z, an A, a Q, whatever. All right. I think that's good for the review. Is it? Yeah. So you should be able to integrate for. Oh, OK. So just one more thing about this. So definitely you should know how to integrate x cos x. How about x squared cos x? How about x sine x? Or x squared sine x? Or x e to the x? Or x squared e to the x? Or ln x, for example. All things you should be able to integrate if you had to. Use a what?
Tabular method?
A what method?
Tabular? Like a table that we use?
That shortcut? Yeah. Yeah, if you know it and you can do it right, then sure. All right, so that does it for test prep. Yeah?
On the midterm, are questions going to be graded, will they be given partial credit, or is it all or nothing?
Yeah, there will be partial credit. Yeah.
Is the midterm going to be during lecture on Wednesday?
Mm-hmm. Yeah, it'll be during lecture on Wednesday. Yeah.
Did you say you want us to bring a blue book, or will it be?
You don't need a blue book. I had them printed out on like 600 sheets of paper, so you guys will have plenty of paper. Okay, so what we're doing now is in the supplement, right? If you paid attention to the class website, you've noticed that some of the material in this class is not in the textbook, but it's in this separate thing called the supplement. Yeah? Integrals of what? No, we haven't done that. I don't think. There's a homework problem on that? Yes. Then send me an email and tell me which homework problem that was. Unless you know, do you know? What was it called? Which homework problem was it called? Or what number was it? From the latest homework? Okay. All right. I'll check it out. Okay. So for the supplement now, so what you guys should do is go to the class website and download the supplement so that you can read it. There's homework problems on it that you don't have to turn in, but you definitely need to know how to do. And today it's on complex numbers. So I'm assuming like most of you guys have seen complex numbers before. Anyone not seen complex numbers? All right, so this will be kind of review right now. Let me first give my little speech on sort of like the motivation for complex numbers, like why they're so cool. Like, did you guys know that the ancient Greeks didn't used to believe in the existence of negative numbers? In fact, they didn't even believe in zero for a while, but eventually they realized, okay, it's really useful if we have a number that's zero, and the old-fashioned Greeks were like, what? How can zero be a number? You can't even see it. But it ended up being really useful to have zero as a placeholder. And then when, say, like one Greek landowner owed 20 sheep to his brother Pythagoras or whatever, you could say he had a negative number of sheep, right? So it was a really useful concept, this idea of negative numbers, even though you can't see a negative, like I can't show you like here's a negative number of sheep. It doesn't really exist, but it's a super useful mathematical concept. So it's as real as a mathematical concept as there is. And originally, we had positive numbers, positive integers, which started off by like counting the fingers on our hand, right? And these solved very simple polynomial equations like x minus n equals 0, where n was a natural number, a positive integer. But then, when we started needing to solve x plus n equals 0, that's when we started needing negative integers. Okay. But eventually, like, For example, let's say, I don't know, I owed my brother like a sheep, but I ate half of it, right? So I was only able to give him half of one. I still owed him half a sheep, which means we need fractions now. So in other words, rational numbers were introduced to solve stuff like x minus, I don't know, n over m equals 0. Where again, n and m are integers. But even that wasn't enough, right? We've gone from the natural numbers to the integers to the rational numbers. What generalization did we need to make next? Irrational, yeah. So even this wasn't good enough if we had to solve, what about like say x squared plus, or x squared minus 2 equals 0. This number, for example, ended up being useful. Like let's say you had a square plot of land, right? And one Greek dude is right here, and he has to bring a sheep all the way to his brother over here. How far does he have to walk if it's 1, mile by 1 mile is root 2 miles. So you can see there was definitely motivation for learning the irrational numbers to solve equations like this. And then we get to equations like this, x squared plus 1 equals 0, which, again, for a long time, people didn't think had any solution. They would just say, there is no solution. Except, it would be really nice if there was, because then we could have this theorem, which I'm going to show you guys within like the next week, called the fundamental theorem of algebra, which says that every polynomial can be totally factored. Like if it's an nth degree polynomial, then it has exactly n roots. It's a really elegant and convenient theorem of algebra, but we can't solve it unless we introduce a new system of numbers, the complex numbers. And that allows us to solve equations like this. And even though they're called imaginary, like they're just as real as a mathematical concept as anything. Like I was just sitting in a physics class today on electricity and magnetism, where they represent electric and magnetic fields are very, very commonly represented as complex numbers, even though it represents like a very real thing, right? Like the electric field at this point has a certain strength and direction. It's a real quantity. Place a charge here. The charge will move under the influence of this force. Nevertheless, it's super convenient to represent these physical quantities with complex numbers because of the mathematical simplifications that it allows. So looking at this equation, we're just going to, or at least if we were the people that were inventing complex numbers, we would define this number the imaginary number, which we will call I for imaginary, as the solution to x squared plus 1 equals 0. I.e., in other words, I squared is -1. So you can take that to be the definition of the imaginary number I. I just want to point out, notice that if I satisfies this, -I, if you square that, right, so that's -I times -I. The negative signs cancel each other out, and it's the same as I squared, which is also -1. So anyway, maybe I shouldn't have said the solution. Maybe I should say a solution, because there's two of them, actually. Anyway, either way, it suffices to take this as the definition of I. And then using that, we can define a complex number z as z is equal to a plus b times I, where a and b are real numbers, any real number. So in fact, a and b can both be 0, or one of them can be 0. So notice that if b is 0, then z equals a is just a real number. So my point is, all the real numbers are also complex numbers. We denote the set of complex numbers by a big C, a blackboard bold C. So the previous remark could be interpreted as saying, set theoretically, this remark says right here that the set of real numbers is contained in the set of complex numbers. Was what I was saying right here. Right, you guys seen all these guys? How this is n, z, q. Now we're up to r, and now we're up to c. If you guys are interested in your mathematical set notation, so set of complex numbers. If a is 0, we say z is purely imaginary. And we have some names. We would call a the real part and b the imaginary part. And we sometimes write a is the real part of z, and b is the imaginary part of z. Let's see. So we can also add and subtract and multiply and divide complex numbers. So can add, subtract, multiply and divide. Now, I could, okay, so let's say if z is a plus bi, how about if w is c plus di? Now, I'm going to write down how to add z and w. Is this a definition, or is it a necessary consequence? Then, right? So I'm saying z plus w, which is a plus bi plus c plus di. I don't know. Like some people say it's a definition. I think it kind of just follows from what we already know about the structure of the real number system. So here's what it is. You add the two real parts, giving you a plus c, and then you also add the two imaginary parts, giving you b plus d times I. And similarly, z minus w, we would just subtract a minus c and b minus d times I. Okay, so that's not so bad. In fact, it might remind you of vector addition, where you add the components. And we're going to see that that's actually a pretty good comparison. But now let's do multiplication. So z times w is a plus bi times c plus di. And if you just distribute, so we'll get an a times c and an a times di and a bic and a bi di. Okay, so that's a times c. I'm going to pull an I out of these two terms. Give me AD plus BC times I. This one, this is BD, and we got an I squared. Which means, what should I do if you see an I squared? Make it a negative 1. So, yeah, that's going to become negative BD. So that's why I actually get minus BD here. Okay. So that's multiplication. What about division? So like if we have z over w, that's a plus bi over c plus di. This is one of the first tricks that you need to learn about complex numbers, is how to deal with fractions. When we have a complex number with a I in the denominator, here, look, like when I just gave you the, where was it, the definition, I just gave you the definition of a complex number. So let me just ask you a quick question. Is 1 over I a complex number? It's not really, it's not what I just said a complex number was. It's not in this form. So is this one? And in fact, it is. Yeah, in fact, any expression that has an I in it is pretty interesting. You can always get it in this form. It's just sometimes there's a trick involved. And the trick here, in this case, is you just multiply by I on the top and bottom. So we get an I, well, 1 times I, which is I on top, I squared on the bottom. So that's I over negative 1, which dividing by negative 1 is the same as negative I. So in fact, it is. It is a complex number. It just didn't quite look like one at first. But we're going to have to do a similar trick right here. And the trick is to multiply. It's going to be something like this, but I'm going to have to do one thing. I'm going to multiply by c minus di on top and bottom. So on the top, I'll get a plus bi, c minus di. On the bottom, c plus di, c minus di. So the top here is, well, okay, I can just multiply these guys. That's an AC plus BD plus BC minus AD times I. But on the bottom, recall the formula that says that like u plus v times u minus v is u squared minus v squared. So it's going to be, I'm going to get a c squared minus di squared. But that's the same as c squared plus d squared. So I get a c squared plus d squared on the bottom. pay attention to that trick that I did right here. This is something you're going to have to do many times over when dealing with complex numbers. I used this identity, and I used the fact that I squared is -1 to rewrite this product as this. And now, this is in the usual form of a complex number, right? This is AC plus BD over C squared plus D squared plus BC minus AD over C squared plus B squared times I. So that is how you divide complex numbers. And this trick that I had to do right here, of where I multiplied by C minus DI, that is so common that there's actually a special name. So this guy right here is called the conjugate of C plus DI. So definition, if W is C plus DI, then the conjugate of W, it's written as W with a bar over it, is C minus DI. Right? Or in other words, C plus DI bar equals C minus DI. Anytime you put a bar over a complex number, it just flips the sign of the imaginary term. And yeah, we just end up having to use that a lot. So here's a few properties of conjugation. For example, if you take the conjugate of the sum, that's the sum of the conjugates. Conjugate of the difference is the difference of the conjugates. Conjugate of the product is the product of the conjugates. Conjugate of the ratio is the ratio of the conjugates. It's all kind of nice, right? Like in each case, it just kind of does exactly what you would hope it would do. You can, by the way, all of these are provable, by the way. I'm not showing you the proofs right now. I encourage you to verify them for yourselves if you're not sure why they're true. And also, in fact, if we take a complex number and multiply it by its conjugate, so that's A plus BI times A minus BI, and as you just saw, this gives us A squared plus B squared. We can define the length, or it's got a few different names. Sometimes people call it length, sometimes people call it magnitude, sometimes people call it absolute value, which I think is a good name because it, in a very real way, represents the distance of a number from the origin of z, as we use the absolute value symbols, and it's the square root of z times z bar. So that's the square root of a squared plus b squared. And this, if you plot a complex number in the plane, where this is the real axis, and this is the imaginary axis, so if like this is A and this is B, then this represents the number A plus BI, then what we just found here is exactly this distance, where this number is Z. So that's why we use absolute value. Just like in the real number system, it's distance from the origin. And we're going to come back to this picture, by the way, and you'll see how this all ties in with polar coordinates, which is why I'm doing it right after I did polar coordinates. And we'll pick that up on Friday.